All right, this is Pre-Calculus Unit 2, Lesson 6. We are examining the graphs of inverse functions. This is a case where I probably know too much and gave away the hen house because I've already talked about the graphs of inverse functions in the context of graphs, of graphing. That said, we can certainly review the concepts we've already talked about. But the idea is this, that when you switch x and y, let me pull up Desmos. When you switch x and y, you get a particular kind of symmetry. Okay? Here, let me get Desmos up. Okay, here we go, graphing calculator. All right. And so I'm just going to use a table to graph some points here. So let's do 0, unlock 0, 1, 2, 3, 4, 7, 5, 4, 6, 2. Okay. And actually let's 1 or 0. Yeah, that'll do. All right. Okay. And if I graph now another table, graph now another table where I invert x and y. So we're going to do 7, 5, 0, 6, 2, 0, 1, 2, 3, 4. Okay, and let's do this one in red so the colors contrast a little bit more. Okay, and let's do it in standard here so it's a little bit more visible. And let's make sure I did it correctly. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 7, 5, 0, 6, 2, 7, 5, 0, 6, 2. Yep, that's right. Okay. And as you look at it, particularly if I draw the line y equals x, okay, particularly if I draw the line y equals x, you'll notice there's some symmetry to these dots, right? Kind of forms the wings of a bird, if you like, on either side of this, right? And that's natural anytime we're talking about inverse functions. When you switch the x and the y, you have symmetry across the line y equals x, right? Okay. So that said, here we can demonstrate this with functions as well. Leave y equals x here. Let's say we've got y equals x cubed plus 7x squared minus 3x plus 4. Right? And here we go. We've got that. Okay. And let's squeeze it here. I'm going to multiply the whole thing or divide the whole thing by 10. There we go. So that'll compress it a little bit, so it's more manageable in our window. All right. So I want to graph the inverse. And this is one thing that Desmos will do. I'm not sure a TI-84 or other graphing calculator will do. I can just rewrite this equation by switching the x and the y. So x equals y cubed plus 7y squared minus 3y plus 4. All over 10. Okay, and lo and behold, there it is, right? We've got a kind of looks like a vase, right? There's this symmetry across the y-axis. Now, one of the things you will notice about the red graph is it's not a function. If we tried to solve it for y, we would get in trouble. We would be unable to solve it for y, and that's because it is not one-to-one. Right? The original function is not one-to-one. One-to-one, if it were going up, it should continue up over the entire duration of the domain. It should never go back down, double back down, because it would fail the horizontal line test. Every unique input must have a unique output. All right, now that said, let's say we're given this task here. We're given a graph, and we're given a function, and we're asked to graph the inverse of it. It's kind of a fun exercise. So grab a sheet of graph paper and follow along here. See if you can do your own. But I'm going to just graph a function without a function rule. All right, I'm just going to graph a function without a function rule. So x, y. Here we go. Let's go red here. All right, we're going to go up like that. Okay. All right. So there's a function we'll call f of x. We want to graph the inverse of f. Okay. So here's what we do. We graph the line y equals x on our graph. Okay. And we pick some points, right? Pick some points. There we go, right there. Right there. And what we're looking for is a function that is symmetrical to that axis. So one of the points I can pick out real easy is right here. Where the original function hits y equals x, the reflection of a point across the line that's on the line of reflection is still on the line of reflection. Okay, I can also get this point here, right? This point is 1.5 diagonals away, so it's 1.5 diagonals away. Okay. This one is 1 diagonal away, so 1 diagonal away. Okay, this point, let's see, 2 diagonals and a little bit more, 2 diagonals and a little bit more. Okay, 1, 2, 3, 4, 1, 2, 3, 4. Going to go off the graph here. And there's no more room up there. Okay, and we can do that for a few other points. We could plot a point, right? This point here. This point here is the point 2, 4, 5, and 1.5. So we're going to go 1.5 and 2, 4, 5. Okay. All right. And so we've got it here. So let's sketch it by hand. Being a little careful. Now this particular function has an inverse because it is constantly going up. Okay, I need another point over here. How about this point here? So 2, 4, 6, 8, 10, and 3. So 3, 2, 4, 6, 8, 10. There we go. All right, we got it. All right, so this would be f inverse of x. Okay, two big takeaways. We're switching x and y when we're doing an inverse. For a function to have an inverse, it has to be invertible, so it has to be 1-to-1. 1-to-1 means every unique input has a unique output. If it's going up at any point, it must continually go up over the entire domain. If it's going down at any point, it must go down over the entire domain. It cannot double back on itself. And we simply reflect every point directly across the line y equals x. All right, that's pretty much it. Let me know if you have any questions.